I'm Kirk Borne, and today I'm going to talk about the intelligent edge and event science. So currently I'm the Chief Science Officer at a new startup, DataPrime, which helps job seekers in the data professions to find the perfect job, and talent acquisition specialists who are looking for candidates to find the perfect candidate using AI. So today I'm going to talk about some of those applications of AI, but specifically those applications at the edge. So here we go. I'm going to turn off the webcam at the moment, so you don't need to see my face on every slide, and we will continue. I like to begin with a story, and begin the story with a quote. So here's the quote from famous baseball philosopher Yogi Berra, who was a pretty funny guy, and he said a lot of funny things. And one of those things he said was, "You can see a lot by just looking." You'll see in a second here why this quote is relevant to the story I'm about to tell you, and it's not really a data science story, but you'll see soon how it is relevant to data science. So the story goes back to the 1950s with a Formula One race going through the streets of a European city. I believe it was in Italy at the time. So the image you see in this graphic, the photograph here, is from London, a Formula One race a few years ago. So this is not a picture from the 1950s, but it's just there to illustrate the point. So the race goes back to the 1950s, and something spectacular happened in that race that made it very memorable. And what's spectacular about it was there was a multiple car pileup. There was a multiple car crash in this race. So what happened during the race is a particular Formula One race. You go through the streets of cities, big cities, and there's long straightaways where there's huge crowds along the side of the street, and the cars come racing by very fast. And when they get to the end of the street, they have to make a sharp turn down another street. So the cars slow down very quickly to make that turn. But the problem with making a sharp turn like that is you can't see around the corner. You can't really see what's coming, unlike on a big oval racetrack for typical sort of oval racetrack type of car races, where you can see far ahead of you what's happening on the oval. And when you're in a city street, you can't see around the corner. But anyway, so this accident happened right around one of those corners. The cars came really roaring fast down the street, that straightaway, with the crowds cheering and everything else. And then when they come around the corner really fast, even though they have to slow down, they're still trying to make that turn as fast as possible. And there was a crash just around the corner that they couldn't see, and they ended up crashing. So there's multiple cars ended up in this crash. But there was one particular driver, when he came down that straightaway, he did slow down like the rest, but when he made the turn, he made a wide turn, not a sharp turn, and he was able to avoid crashing into the cars that were already there, and he went on to win the race. So during the press conference after the race, he was being congratulated for his marvelous driving skills. And he was shaking his head saying, no, that's not really what happened. So they said, well, what did happen? That's what we saw happen. And he said, no, what really happened was something I didn't understand at all at the time. But he said, but after the race, he said he now understands what happened. And what happened was, as he was coming down that long, fast straightaway before the turn, with the crowds there watching the cars go by, he realized the crowd was not looking at him. The crowd's heads were all turned looking down the street, which is very unusual, because normally when the cars come roaring by really fast, the crowd is cheering and they're watching that car, and their heads are watching that car, and their heads turned with the car as it passes by. But the people were looking down the street, not at him. And so he knew something was wrong just intuitively, even though he didn't realize it at the time consciously. So subconsciously, he knew there was something was wrong. And so when he got to the end of the street, he made a different sort of a turn, a wider, safer turn, instead of a sharp, fast turn. And he was able to avoid the crash and win the race. So what was going on here, and what makes it a data science story in my mind, is that he had additional sensors. He had contextual sensors in his environment, telling him what was going on, and in fact, what's coming around the corner, almost like a forecast. These people could see what was around the corner, and though he couldn't see it, the sensors in his environment, that is, the people in the audience, these sensors in his environment were able to see what was coming around the corner. So in a sense, he got a forecast intuitively, subconsciously, without him even knowing it, from these contextual sensors in his environment. And so intelligence at the edge really is based upon not just the data that we're getting off of particular sensors, because that's just a data stream. But what's really important is we get the contextual signals from other sensors in the environment, other things happening in the environment, not just from the one sensor that you're collecting data from. So another way to say this, another famous guy, Leonardo da Vinci, several hundred years ago, he said this, something similar to what Yogi Berra said, but maybe a little bit more philosophical and reasonable. That is, learn how to see. He said, learn how to see, realize that everything connects to everything else. And those connections are the context we're talking about. Context, therefore, is really critical in intelligence and in sense making. And numerous articles have been written about contextual intelligence, how contextual knowledge, contextual data makes AI smarter, whether it's using graph models or other types of techniques to connect the different pieces of information flowing from these additional data sources. So at the edge, we're talking about different sensors providing the context, providing the knowledge. And as we find what the connections are and the relationships among those different data streams, then we actually build up that intelligence and sense making, which give us ultimately the intelligent edge. Now, talk about context. I want to put this in the context of emerging and disruptive digital technology trends. And Lord knows that there is a lot of emerging and disruptive technology trends, especially digital technology trends. And you see a graphic here. It's probably too hard to read all the words on that graph. So I'm going to highlight some of them. And these are, the next slide, you'll actually see some of the words from this slide highlighted. Here you go. A lot of these words are, you can't see now because on the actual graphics, so I put them in these red boxes, and you'll see all kinds of things: drones, digital twins, Internet of Things, machine learning, and on it goes. So I would say this is what digital transformation, or rather digital disruption, actually looks like. It's really incredible what's happening in the world. Data everywhere. So this rapidly expanding frontier of emerging technologies are basically innovations inspired by data, informed by data, enabled by data, and create value from data. You see quite a few things listed there, and we're going to describe a few of them as we continue. So here they are. First, we're going to look at these intelligence edge applications, starting with model monitoring and AI itself, of course, as an intelligent edge application. And then we'll pick off some of those things from the previous slide that I mentioned: robotics, drones, autonomous vehicles, 3D and 4D printing, virtual reality, augmented reality, immersive realities, and ultimately the Internet of Things, which I would like to call the Internet of Context. Going back to that story about the race car, that all of the sensors in your environment, including the sensors that make up the IoT, Internet of Things, provide us with that context, a contextual intelligence to give us a truly intelligent edge. One of the most relevant edge intelligence applications for data scientists is this one: model monitoring. When we deploy models in our environment, we're deploying them at some place where operations are happening. So that's an edge application, whether it's actually an e-commerce store or a self-driving vehicle or a camera or a drone or something, anything of that sort. That's truly an edge application. And embedded in that are models that fuel the AI that derive the action that the AI will take. And so we need to monitor our models to see if they're behaving properly as things change in the world. And so we call this model monitoring. And what we're really monitoring, not just the model itself, but the two components of a model, which are the input, the data, and the output, which we call the concept. All right, so the data drift, the input, and the thing that we're trying to model, that is, we're trying to produce the output, the classification or the prediction, that's the concept. So this is at the edge, of course, because we're talking about an operational endpoint of one of our ML or AI applications. And there are many examples of this during the COVID era, which we'll talk about in a second here. But let's talk about what we mean. So a model is nothing more than a concept of mapping an input to an output. Okay, mapping an X to a Y through some function X. So data drift refers to changes in the input, changes in the X. Concept refers to changes in the thing you're trying to predict, the thing you're trying to classify, the thing you're trying to get right. And if that changes, that's called concept drift, and that's basically changes in the Y. So model drift is basically the consequences of all these things in some complicated way that we need to sort out. So different kinds of strategies we apply for model monitoring include data ops, ML ops, model ops, and observability. And there's plenty of talks on these. I don't have time today to go into details, but we will come back to observability at the end. So the examples during the COVID pandemic era have been pretty substantial. And there's this article, which I have a link to here, that's titled, "Our Weird Behavior During the Pandemic is Messing with AI Models." So there's so many applications of model monitoring that needed to be in place during the COVID era. But before I start with that list, I just want to show a little cartoon here, which is not specifically about model monitoring, but it just sort of reminds us again that digital transformation and digital disruption are sort of like two sides of the same thing. And this is a cartoon from the marketunist, Lawrence Fishburne. He does a lot of really great cartoons, especially in the marketing field, but that applies to a lot of things. And of course, we see the people sitting in the boardroom and they're saying, "Hey, digital transformation is years away. I don't see our company having any change, having to change anytime soon." Okay, of course, while they're saying this, here comes the wrecking ball called COVID-19 that's going to truly disrupt that business. So back to the real world. Here we got the COVID examples of model failures. And what I mean by model failures are both anomaly detection models and also prediction models. So there's a combination of many different types of models that failed pretty horribly during the COVID era. Number one, the consumer buying habits, as we could all imagine. And that, of course, affects manufacturing and retail supply chain because people are buying and demanding different things. There's also the anomaly detection models that are wrong, like cybersecurity issues or fraud issues. For example, insurance claims. I think for myself alone, I was a victim of 3 different unemployment insurance claims in 3 different states in the United States during this era. And I had to basically contact those organizations and make sure that they didn't file the claim because it wasn't from me. Also, home and business network and energy usage. I mean, the predictive models on how we use our networks and how we're using energy, both in businesses and homes and office buildings, completely changed. Clearly, there was enormous changes in the predicted patterns in traffic and travel industry. How decisions are made about pricing travel. Everything changed dramatically. And even the service industry workforce prediction models were a complete disaster. I mean, I remember talking with a group that they were working with one of these food delivery companies, right? Basically, people use their own cars to deliver fast food to homes, to individuals. So you go online, you use the app, you order something from a restaurant, and these people who provide a service will deliver to your home. But as part of that service, part of that organization providing the service, they have a call center where consumers can call up to complain or to ask about their account or ask about the services or whatever. And so this particular food service delivery app, its call center, they were saying that they traditionally had an 80-person workforce. That is, the people who monitor the phones at their call center for customer calls. They typically would have 80 people in their entire workforce that they would schedule throughout the week, and they had a model about how much demand they need at different times of the week, like weekends or Friday nights or something like that. The number of people would be on duty at the call center. Well, what they discovered once all this, everybody was working from home and eating from home and asking someone else to bring the food to their home, that they had to suddenly increase the number of call center representatives in their call center. And how bad was it? Well, they went from having 80 total employees, 80 total employees that they used and distributed around the week. They were suddenly hiring 100 new call center representatives every day. They were hiring 100 new employees every single day, when before they could operate their entire business throughout the week, throughout the month, throughout the year, with a total of 80 people. So clearly the workforce prediction models were a complete mess in terms of what times of week, what times of day, which days of week they had need a particular number of people to be at the call center. Everything completely changed. So these are all examples of model failures where the inputs and the outputs were being seriously affected. Both the data that was being used to train those models was no longer the same data that's representing how consumers are behaving during this period, and consequently the output of the models were not only wrong, but they were probably not even applicable to the situation at hand. So as I said, AI itself by itself is indeed an edge intelligence application because it is an artificial intelligence we're talking about here. So it's using edge data to inform and to initiate actions. And I just list a handful here. Clearly, I'm not going to spend time talking about each one of these in detail, but examples. For example, postal code readers that scan letters and envelopes to detect digits to recognize the postal code. That's an application at the edge. Email spam detection at the point that you collect the email comes into your folder and you're collecting it, whether in the inbox or the spam folder. The spam detection is critical. Disease detection and medical diagnostics. Oftentimes now, because of the power of deep learning and AI models, you can actually do pretty real-time disease detection in medical data, medical diagnostic data. Location intelligence, that's what's going on right now, whether you are or where a vehicle is or where a truck delivery person is. Location intelligence is truly an edge intelligent application. And again, we go to logistics, supply chain, inventory, and workforce management, some of the things I was just talking about. Even conversational bots, okay, conversational AI. I mean, it has to work right there in the moment as you're talking with the chatbot. Right? It has to respond to in that moment at that place where the conversation is happening. Online product recommendation engines, same thing. When you're at that point of sale, at the point of interacting with the e-commerce store, the recommendation happens at that place at that time. Fraud alerts. We want real-time fraud alerts, both in the financial world as well as insurance world. Cyber benefits applications, things of that sort. Fast response is essential in cases like this. And ultimately, anomaly detection is a broad category of things, whether it's, again, in these insurance claim applications or cyber applications, but also in engines and motors and devices of all types, activities, the sort of behavioral activities of people as they move through for example, sporting events or entertainment events, being able to detect anomalies. Now, all these applications I'm talking about here are not inclusive of the COVID era. These are applications of AI that can be part of an issue we're having in the COVID area, but just in general applications of AI at the edge. So now getting into some of those emerging technologies, robotics. These are obviously devices that move and react to sensory input, and specifically that sensory input is edge data from sensors, whether it's assembly lines or the Roomba who cleans your house, or prosthetics, warehousing, logistics, autonomous exploration, whether in deep space, like the Mars rover there, or deep sea, or remote environments. These are all edge data from sensors that give sensory input to devices that move and react in their environment. Drones. Drones are nothing more than a flying robot, basically. They can either be remotely controlled or fly autonomously through software-controlled flight plans and onboard edge sensors, including GPS. So the applications of drones, we know plenty of those: search and rescue, civic applications, disaster response, even overseeing large construction projects, military operations, fun, of course. And another robot, if you want to think of it that way, robotic application, autonomous vehicles. So these are self-driving intelligent edge vehicles and systems that are informed by data that are streaming from many different types of edge sensors, cameras, radar, LiDAR. So these sensors feed algorithms that feed operational controls in this system. This happens to be a vehicle that helps it to make autonomous decisions and take actions based upon the data-fed algorithms that are embedded within the system. 3D printing. Well, we know about 3D printing, and not by itself, and you may not think of that as an edge application, but as it moves to more dynamic printing, which we call 4D printing, then it's actually taking inputs from edge sensors and actually printing out, and by printing, I mean it's actually being able to change the shape of the device or the product in real time in response to the sensors data that are inputs to the algorithm that adjusts the shape of the thing. Now, if you don't know what I'm talking about, look at that YouTube at the bottom left, this TED Talk that talks about how people are using carbon nanotubes as stents, heart stents in people's arteries, heart arteries, and the carbon nanotubes are attached to the sensors which are measuring the condition of the person who has the heart stent. I mean, for example, their blood pressure, maybe their blood pulse, their body temperature, a number of different sensors in the body, detecting whether the person is under stress or not under stress, and you can actually change the shape of the heart stent to the most healthy shape it needs to be under different stressful conditions that the patient has, and it's using the sensor data from all those wearable device sensors, and it's actually using electrical impulses to change the shape of the carbon nanotube. So in a sense, it's not a traditional like concept of 3D printing. It's not printing out on a printer, but it's actually using information to create a product, in this case a heart stent, which is dynamically changing in shape in response to input from these edge sensors. Pretty amazing stuff. Check out that YouTube. Virtual reality. These are basically computer generated, that is data driven simulations of 3D environments. And as you move through that environment, if you don't have a real virtual reality experience, there has to be edge data collectors and data generators. That is, if you're actually interacting with the environment and seeing it from different perspectives, it has to recognize where you are and what you're doing in that virtual environment. And so these are edge data collectors and edge data generators. And so many examples and applications of this in our world, games and family adventures, and more serious applications, clearly training and education, medical treatment, even in design of products. But for us, we can actually explore our large multidimensional data sets in a virtual world as well. So augmented reality is that space between virtual reality and the real world where you superpose a computer-generated version of something onto your real world. Okay, so you're actually at a place, and again, we'll call that at the edge, whether you're in a store or in a disaster response situation, or if you're trying on clothes. That extra information, that extra data, if you will, is superposed on your real world experience. So you're actually seeing your world, but you're also seeing additional information. So there are many applications of augmented reality, of course, in retail, disaster response, even in some situations of major systems repair and maintenance, where the workers who are doing the repairs have the augmented reality glasses on, so both hands are kept free, while there's actually information projected in front of their eyes as they're doing the system repair, so they don't have to use their hands to be looking through a manual or doing something of that sort. Clearly a similar situation with augmented medical procedures, and of course in video games, and even in security in environments like shopping malls, entertainment, and sports events. You can use augmented reality to identify, for example, maybe people are in maybe medical distress or some kind of anomalous behavior or risky behavior that someone might be having in that environment. And so it actually identifies those people to the security folks without actually taking their eyes off the folks. They can actually get the information projected onto the screen where they're actually seeing the actual people in the environment. Which brings us to our Internet of Things example, where we have sensors on edge devices and sensors everywhere, devices everywhere. So this is our sort of ultimate example of edge intelligence, where we get this edge data from all these sensors, which fuel these machine learning and AI models and applications, including all the things we were just talking about. I mean, all these different types of things of robotics and drones, AR and VR, autonomous vehicles. In a sense, these are all examples of Internet of Things. That is, there's actual data that's streaming from sensors into these actionable devices of one kind or another. So Internet of Things, like I said, is sensors and data collection everywhere. So I like to say the Internet used to be a thing. Now, things are the Internet. So this Internet of Context, again, reflecting back on the story of the race car driver at the beginning, is an example where we basically are fueling, giving contextual intelligence to our decision-making applications, to our AI-driven decision-making and actionable intelligence applications. And so several books have been written on this. I like these two that I show here, The Age of Context and Outside Insight, which are both talking about that contextual intelligence that comes from additional data sources, not just the immediate data source in front of you, but those external sensors. So the race car driver was able to avoid the crash because he wasn't just using his own eyes to see straight ahead, but using the eyes of all the sensors in his environment, the crowd, to actually make a better decision. Now, I don't think this scene was actually in the Toy Story movie, but I like to think so. Context everywhere. Context to infinity and beyond. So what's coming in our world is this explosive growth in both Internet of Things and the industrial Internet of Things. Just a few numbers on these slides. There's actually sort of projections in the trillions of dollars for revenue from the Internet of Things over the next decade. Nearly $1 trillion predicted by the Linux Foundation's Edge Foundation report. They talked about nearly $1 trillion in edge computing revenues by the year 2028. And even another article, which I link at the bottom, that says Internet of Things companies will dominate the 2020s. Is your resume ready? So the Internet of Context, I call that the power source for contextual intelligence and for event science. We're going to say a bit more about event science next. But this power source for contextual intelligence gives us, essentially, as we tap into these sensors through APIs or however we get this information, this knowledge, this contextual intelligence from those IoT sensors, they provide context as a service. And even as in the car race, forecasting as a service, seeing around corners, if you will, insights as a service, and essentially intelligence edge as a service. So event science is basically the application of our data science and machine learning to triaging events, determining what are the most critical things that we need to respond to, which things we don't need to respond to, sort of typical triage. If you get an alert about something, is it an alert that needs immediate reaction, or something that you just file away as informational alert, that is, it doesn't require immediate reaction, or maybe it's alerting something that's normal and you just need to know about it, but it's not necessary to take immediate action on it. And so that these dynamic data-driven application systems, there's actually a website and a project that's devoted to this. And they talk about these 4 steps in going from data to action. Okay, so event science is part of the measurement, inference, prediction, and action, that is steering process, which is determined from all the things that we know and as data scientists. That is, we measure things. We collect different type of data from edge sensors, and there's a big list there. We get edge data. We get all this data, and then we apply our algorithms to see which patterns are in the data are most meaningful, which alerts, for example, are anomalies or deviations in data, deviations in concept, data drift, concept drift, or predicting some kind of behavior or engine failure, or maybe a medical diagnostic in a patient, or whatever. So we apply our machine learning to infer what is going on in the data. We make a prediction, and therefore from that prediction, we make a decision of how to take an action. So essentially, a decision is nothing more than a prediction. You decide to do one thing or another thing based upon what you predict the outcome would be if you choose one or the other decision. So machine learning and AI is the IP, the inference and prediction component of event science. And ultimately, it's an action that's taken at the end. So we call that an autonomous edge process, or an autonomous edge system, where you have to do process automation. So edge intelligence with event science is essentially, they go hand in hand. So if you gather the actionable insights from any streaming sensor data, you automate the event-driven operational system, and that gives you event science at the intelligent edge. Now, sometimes when I talk about event science, people think, oh, you're just talking about monitoring, right? Well, I say it's way more than monitoring. It's more of a scientific process of understanding what are the most meaningful signals the most meaningful things happening in those streams of data, but not just that, but identifying the false positives and false negatives and increasing the accuracy of your alerts, the accuracy of the predictions and alerts that you're receiving from those streaming data. So it's not just monitoring, but it's doing all the things that data science does for you, where you test in your model, you change the features that you're collecting, you do feature engineering, you do model feedback, back propagation, anything it needs to improve the accuracy and precision and utility of the model that you're using to decide a particular action in response to a particular event in your data. So event science is more than just monitoring with sensors and data, because deploying sensors everywhere basically guarantees a data deluge. Yep, that's what we're going to get, a data deluge with these sensors all over the world. But we don't need more information. What we really need is more insights. That's the truth. We really need more insights, not just more information. So to get to those insights in this flood of data, we consequently need smart edge deployments. Now, what do I mean by smart? Well, they're smart in numerous ways. First of all, they're cognitive. They're contextual and predictive of the types we've been talking about already. But beyond that, they're also smart in the business sense of being informed. That is, the deployments themselves are informed by deliberate decisions about where and when more insights are needed. Where sensors and data are needed in your enterprise, making an informed, intelligent, deliberate decision of where and when to start collecting data. And so these decisions, hopefully these deployments, therefore, are strategic in order that are designed to meet desired outcomes and mission objectives for the enterprise. Therefore, you need a strategy, and I call this the observability strategy. Where and when are we deploying sensors and collecting data in order to deliver that mission-critical insights as a service for your organization? So the bottom line is this. Monitoring is what you do. Sensors are how you do it. And observability is why you do it. So that observability strategy talks about why are we collecting data here? Why are we collecting this type of data in these places? So the insights from this event data are consequently the rewards for doing this. And what you can do is you can add APIs to these sensors and actually create a business model where you're providing insights as a service and context as a service from your observability strategy to other units within your business or even to your external vendor partners that you are working with, getting access to those sensor streams in order to get context and insights, even forecasting as a service. Without a doubt, there are limitless machine learning and event science opportunities at the edge. Here's an article and a graphic from that article which discusses some of these things, many of which we've already talked about. The good news is there's also tools and algorithms that work for edge intelligence. That is, they have a tiny footprint in terms of the algorithm and the actual hardware needed to do intelligence at the edge in many of the real-world operational deployments that we've been talking about. So here's some resources you can check for that. So in summary, here are 3 analytics applications at the intelligent edge. 1, Sentinel Analytics. The Sentinel is the thing that gives you the warning, the alert. So it's using sensors and data to watch the things that should be watched to be assured that things are working fine. I'm picking up good vibrations or not. So the Sentinel is the guard on the guard post that tells you things are fine or we need to sound the alarm. Number 2, Precursor Analytics. Detecting the early warning signs of risky events. Drifts, change points, and emerging trends, oh my. Data drifts, concept drifts, change points, and emerging trends, oh my. That's forecasting as a service when you get those early warning signs, those precursor signals. Number 3, cognitive analytics. That is actually discovering the right questions you should be asking in your data. For example, when you see something funny in your data, what questions should I be asking? When I see an anomaly or a trend or a correlation or something that's changing, what should I be doing? So asking the right questions. That's cognitive event science. So thank you. Come for the data, stay for the science. I love to end with this quote from Isaac Asimov, one of my favorite quotes, where he says, the most exciting phrase to hear in science, The one that heralds new discoveries is not Eureka, but that's funny. So I'm wishing you many funny encounters with your data. And while you're doing that, you might want to check out this book, which I co-authored, which will be appearing in print later this year. So thank you very much.